board. All right, so 6.3, factoring special products is what we'll be learning about today. I will say this is a lesson that is a little bit more on the challenging end. So if you do need to go back and rewatch this video lecture, I strongly recommend it. And I'll try to make it as simple as possible. But there's a lot of just special products that you're going to have to practice over and over again so that it really solidifies in your mind. And you can pick them out through workbook problems, through your MyOpen Math homework, as well as through your assessments, either quizzes or your exams. Our learning objectives for today are the following. So we'll be able to factor our perfect square trinomials, and I spelled perfect incorrectly. It's kind of funny. We'll be able to factor the difference of squares, and then we'll be able to factor sums and differences of cubes. Right, so let's start with some warm-up problems. Our first question is asking us to simplify this monomial. So we really want to utilize some properties of exponents here. What do you think we get for 3x squared in parentheses cubed? Are we distributing that 3 to both the 3 and the x squared? Yes, we are. So this is another way of writing 3 to the third and then x squared raised to the cubed. And when you're raising something, what are you doing with those exponents? Not adding, you're actually multiplying. You're adding when, for example, let's say you're looking at x to the third times x to the second. So when you're multiplying two terms that have that same base, then the rule of exponents tells us to add those exponents. I should say the properties of exponents tells us to add. Whereas when you're raising it to a power of 3, you're actually multiplying those exponents. So we have 2 times 3, which gives us 6. So we're looking at x to the 6th. And then 3 to the third is the same as 3 times 3 times 3, which is 27. So our simplified result is 27x to the 6th. And maybe shrink this and put this off to the side so that we can look at our next one. And then, let's see, Chris, in case you want to submit it late onto Gradescope. Okay. Our second warm-up problem, we are asked to multiply these two binomials. So again, this is sort of our practice of either utilizing FOIL or what we'll learn today and practice our difference of squares. And so we'll first do it using FOIL so you can really understand what I'm talking about here. We have our x squared plus 3x. Then we have a minus 3x. So what do we notice about those middle terms? And then a minus 9. So anytime we're dealing with difference of squares, those middle terms actually end up canceling out. So essentially, we just look at that first term and that last term, which is expanded into our x squared minus 9, and we're done. And how do we sort of realize that when we're just looking at the binomials themselves? Well, we have a minus 3 and a plus 3. That same value, but they're just opposite signs. And then finally, we have our third example where we're looking at a perfect square trinomial, but instead of it being difference of squares, we have our binomial of the same operation and same value twice. So instead of those middle terms canceling out, it's actually going to be doubled. So we could technically do it in our head at this point instead of foiling. Our first term, m times m is m squared, And then we have this 4m that we just double. What's 4 plus 4? 8. So we have that plus 8m. And then our last term, 4 times 4, is our constant, which is that plus 16. So, but we'll continue to practice this throughout loads of examples in this lesson. We'll even get up to dealing with cubic functions, the sums and differences of cubes. But let's focus on squares for the time being. Any questions at all? No? Okay. So we have a notes page, and maybe I'll have a student read. James, do you want to read this part for me? And then maybe I'll have William, you can read that second part.
Some trinomials are perfect squares. They result from multiplying a binomial of the square of binomial using the binomial squares pattern in the previous chapter.
And then William.
The trinomial 9x squared plus 24x plus 16 is called a perfect square trinomial. It is the square of the binomial 3x plus 4.
Good, thank you guys. So a way to sort of really pick out perfect square trinomials is you kind of want to think of your perfect square numbers, right? 1, 9, 16, 25, 36, 49, 64, 81, and it just keeps on going. So, 9, 16, those are both perfect squares. So you could probably factor this into a perfect square trinomial. And this is just an example of looking at it from its factored form versus its expanded form. And so our perfect square trinomials pattern are when we're dealing with the sum of the two binomials versus our difference of the two binomials. So anytime we're looking at perfect square trinomials patterns, they share that same operation. We either have a plus b in parentheses squared or a minus b in parentheses squared. And what does that end up expanding out to? Well, if it's a plus, then those middle terms are being added to one another, so that operation is positive. And if it's a minus, then those two terms are still doubled, but instead of the operation being positive, it's negative. And then this slide is just sort of like the step-by-step procedure in breaking down those expanded forms of those perfect square trinomials into our factored form, either a plus b in parentheses squared or a minus b in parentheses squared. And we will practice this utilizing some concrete examples. The first one being example 1, which is what we have here. So again, 9x squared plus 12x plus 4, look at that first term and that second term. And you'll notice straight off the bat, we have perfect squares. So there's a good chance we're dealing with a perfect square trinomial. What is the square root of 9x squared? Well, what's the square root of 9? 3. And what's the square root of x squared? X. Okay, let's look at that last term. What's the square root of 4? 2. And then what's that operation for that middle term? It's a plus. So essentially, we can just factor this out into 3x plus 2. And then what are we missing? We're missing our little exponent, raising it to the second power. And we're done. Now, if you're not convinced this is the factored form, let's check our work. We have 3x plus 2 in parentheses squared is the same as 3x plus 2 times 3x plus 2. Let's utilize our famous FOIL method. 3x times 3x gives you that 9x squared. 3x times 2 gives you that plus 6x. 2 times 3x also gives you a plus 6x. And then 2 times 2 gives you the plus 4. Let's go ahead and combine some like terms. We have a 6x and another 6x, which adds up to be 12x. And so our final trinomial is exactly what we started with, which means we factored it properly. Okay. Questions at all? So let's move on to another example. In this case, what do you notice about that middle term? It's no longer positive, it's negative. So when we end up factoring, there's going to be a minus sign between those terms. And now let's highlight that leading term of 81y squared. And when we take the square root of that, what do we end up getting? Good. Thank you, Daniel. And now let's look at that last term, which is 16. When we take the square root of 16, what do we get? 4. Awesome. And we're done. Well, actually, what are we missing? We have to raise this to the second power. It saves you a lot of time. Can you pull out a greatest common factor and then utilize the AC method, which you guys practiced loads with in our section 6.2? Yes, of course. But that'll take you probably an extra 2 minutes to facilitate versus a few seconds. And when you're working on an assessment, it's good to utilize your strategies so that you can solve the problems in the most efficient manner possible. Right. So let's do another example together. Square root of 36x squared gives us 6x. Square root of 49y squared gives us 7y. So we're looking at, and then the middle term is positive or negative? It's a positive, so we're looking at 6x plus 7y in parentheses squared, and we're done. And you can always check the problem either off to the side or in your head. If you multiply these two, 6x times 7y, you get 42xy, and 42xy doubled gives you that middle term, 84xy. So you did it correctly. So we have another little comments before we jump into our example 4. Let's see, Said, can you read this for me?
Remember, the first step in factoring is to look for a greatest common factor. Perfect square trinomials may have a greatest common factor in all 3 terms, and it should be factored outwards. And sometimes, once the greatest common factor has been factored, you will recognize the perfect square trinomial.
Good, thank you. And so you can pull out the greatest common factor first, or again, if you know that these are both perfect squares, then you can sort of jump straight into it. However, you can't take a perfect square. Well, you can, but then you're just going to be left with the square root of 100x squared y. Because taking the square root of this, well, you know the square root of 100x squared is just 10x, but then what about that y? And that's where this sort of comment section comes into play. You know that every single one of these terms shares that y. So in this circumstance, it would be in your best interest to factor out that y before jumping into the whole perfect square trinomial. Whereas if we went to maybe back to example 3, I know that I don't think 36, 84, and 49 have a greatest common factor, but let's say they did, you wouldn't have to pull those out because you know that that first and last term are perfect squares, so you can just jump straight into that perfect square trinomial. So once we pull out that y, what are we left with? We have 100x squared minus 80x plus 16. And now we're back to the whole perfect square trinomial. We're looking at that minus sign for that middle term. Off to the side, that leading term, 100x squared, which we can very efficiently take the square root of. That ends up being what? 10x, good. Now let's look at that last term, 16. We can also very efficiently take the square root of that, and we end up with 4. Awesome. And so now we just plug those values in, and we get our fully factored form. What are we missing? Yeah, we want to make sure that we're raising this to the second power. And we're done. Our second objective is factoring the difference of squares. So anytime you see the words difference of squares, that means the operations are of opposite signs. We have a minus sign and a plus sign. And then that also means that the middle terms, our objective is our middle terms are canceling out. So let's see, Angel, can you read this for us?
The other special product you saw in the previous chapter was the product of conjugates. Use this to multiply two binomials that were conjugates. Here's an example.
Good. And so that's just a fancy way of saying opposite signs. Products of conjugates is just you have that minus versus that plus, and the terms that we're looking at are identical. 3x is identical to this 3x. This 4 value is identical to that other 4 value. Another notes page, really looking at the whole difference of squares pattern. The key in dealing with conjugates, once again, is just eliminating those middle terms. And I'll once again write it in because I just think that's the most important thing to absorb. From difference of squares, your middle terms cancel out. Hence the opposite signs. A minus 4x plus a 4x turns to 0. And so anytime you have an a minus b multiplied by an a plus b, all you have to do is take the product of your a's, which gives you a squared, and then take the product of your b's, which is negative b squared, and that is your fully factored form. Right. Down here, this is just saying that difference is another way of saying subtraction. They're synonyms of one another. Right. So before we jump into our concrete example, this is just the formalized steps in factoring the difference of squares, but we'll put this into action on the next slide. So let's look at example 5. We have 64y squared minus 1. Ooh, it looks much easier, right? There's no more trinomial here because those middle terms cancel out. But the process is still the same with finding your perfect square of that first and of that last term. What's the square root of 64y squared? 8y. And what's the square root of 1? 1. So when we're looking at difference of squares, we are actually going to have two binomials. One's going to be plus and the other one's going to be minus. And then we have our terms, our 8y plus 1 times our 8y minus 1. And we're done. I always like to highlight the first major example so you can really see what's going on. Any questions at all? Yeah.
Do we simplify it to make it a squared minus b squared?
You want to leave it like this because the simplified version is what we started with, our 64y squared minus 1. So when we look at it generically, we started with a squared minus b squared, and we wanted to factor this, right? This is in expanded form. And when we factor, it turns into a plus b, in parentheses, a minus b. And so again, this is our expanded form. And this is our factored form. And so we hit the point in the class where you'll be asked to either factor a problem or FOIL out / expand a problem. And that's why really reading those instructions on your exam will determine whether you're solving the problem properly or not. But good question. All right. So another little notes page, which is a very common mistake that I see when we're dealing with our special products formulas. We just learned our difference of squares, how those middle terms cancel out when it's an a squared minus b squared. But if we were looking at an a squared plus b squared, it's actually impossible to factor that out. And why is that? Well, if you have an a plus b and an a minus b, this negative is never going to be positive, right? A negative b times a positive b, a negative times a positive will always, always, always be a negative. So it is impossible to just be left with two terms and have those middle terms cancel out with a positive being squished in between. So anytime you see two terms and there's a plus in between and we're dealing with some squares, you know straight away that it's prime and it's not factorable. Right. Let's do some more examples together. So what do we notice here? Our first term, we can very easily take the square root of that. And when we do, what do we end up with? Yeah, 12x. And then what about that last term? What's the square root of 49y squared? 7y. What's our operation in between? It's a minus, so we can have our two parentheses. This is another difference of squares problem. We have a plus. I have to get a new tip soon. And so let's just fill it in. 12x minus 7y and 12x plus 7y. And we're done. Let's keep going. So we have another little comment section. Let's see, Chris, maybe I'll have you read this for us.
Yes.
practice, guys. So once we get into the more complex problems, we'll be utilizing difference of squares multiple times in the problem. But that first thing, factoring out that GCF, that should always be on your mind because you want to sort of make your life easier. Is there a GCF? Oh, there is. All right, let me factor it out and then proceed. So now we're looking at 48x to the fourth y squared minus 243 y squared. Is there a GCF? Out of 48 and 243, they're both divisible by what number? 243 is a large number, but when you take the sum of it, ends up being 9. Remember that trick from, I think, either our first lesson or second lesson of this course? It's divisible by 3, right? And so is 48. How many times does 3 go into 48? Well, we know 12 times 3 is 36, so it's a little higher than that. 16, thank you. And then what about 243? Well, break it up. How many times does 3 go into 24? 8. And how many times does 3 go into 3? 1. So we have 81. And now out of 16 and 81, are those two numbers relatively prime? They are indeed. So we're done with our cake method. And what do we also notice about that whole 16 and 81? What are they? They're perfect squares, right? So our GCF, well, we have 3, but can we pull out something else? Do they share any common variables? Yeah, they share not just a y, they share a y squared. So we can pull out 3y squared from both of these terms. And so when we do that, what are we left with? Well, 3 times what gives you 48? Our 16. So we have our 16 and then our x to the fourth minus, and then 3 times what gives you that 243? We have that 81. And we already pulled out that y squared on the outside. But are we done yet? Can we factor this out a little bit more? Utilize that method that we just learned about in these past few slides, our difference of squares. We can, right? What is our square root of 16x to the fourth? 4x. Good. And what's the square root of 81? 9. So we're looking at 4x squared plus 9 and 4x squared minus 9. Those middle terms are canceling out. And so now we have this whole expression. But are we done? Remember that notes might be situations where you can use difference of squares twice. Is 4x squared and 9 a perfect square? It is. And 4x squared plus 9, what is that? Can we factor the 4x squared plus 9 more or no? That plus sort of indicates we have prime, right? But this whole 4x squared minus 9 can be broken up into what two binomials? What's the square root of 4x squared? 2x. And then what's the square root of 9? 3. So now we finally arrived at our fully simplified result. Any questions at all? Right. So I will read this next one. We have the next example has a polynomial with 4 terms. So far, when this occurred, we grouped the terms in twos and factored from there, aka our factor by grouping. But here, we'll notice that the first 3 terms form a perfect square trinomial. Right? So oops, sorry about that. We'll write this out. Our x squared minus 6x plus 9, that's our whole perfect square trinomial. And so let's see if we can factor that out first and then go from there. A lot of the time in math is just experimenting and having fun based off of the methods you've learned in class, and then sort of puzzling your way through to see, okay, what can my next step be? So x squared minus 6x plus 9, that middle term didn't cancel out, so we're looking at a minus in between because that middle term is minus. And then what's the square root of x squared? Yep. And what's the square root of 9? So essentially, this is just x minus 3 in parentheses squared minus y squared. But what do we notice? This is sort of like an a squared minus b squared in disguise. And isn't a squared minus b squared the same as a plus b, a minus b? Our a here is just that x minus 3, and then our b is our y. So what can this be fully factored into? We have x minus 3 minus y in parentheses, and then x minus 3 plus y in parentheses. And I'll once again highlight it so you can really see the whole a minus b and a plus b. I almost always see a question like this pop up on assessments. And they like to utilize not just 2 different variables, but they like to use like 2 constants here. So once you get to that point, you can actually combine those like terms. Let's keep going. And so we finally arrived at our last objective for today, which is dealing with factoring sums and difference of cubes. So we're no longer in the 2nd degree, but we're now in the 3rd degree. And these are sort of cubic functions or cubic expressions at this point that you want to get a good grasp of. So I highly recommend creating flashcards of these and practicing all of those workbook problems in section 6.3 because the more you practice it, the more it's just ingrained into your head. The way I like to remember our whole a cubed plus b cubed is whichever sign we're dealing with, that binomial is going to be that same sign. But then when you have a plus, the operation signs are sort of in that palindrome format. So you're going to have a plus, then a minus, then a plus. Whereas if it's just minus, then again, that binomial is the same sign, but then that whole trinomial afterwards is opposite signs. And then all the terms sort of stay the same, that a squared, that ab, and then that b squared, whether it's the sums of cubes or the difference of cubes. This is just sort of the step-by-step procedure in factoring sum and difference of cubes, but we'll go through it together using some concrete examples. And so we'll start with our whole x cubed plus 64. And you'll notice straight off the bat, we have that plus, and I want to make sure that, I think it's pink, or no, it's orange. I want to keep it all color coordinated. And so off to the side here, we have our a cubed plus our b cubed. And again, that first binomial, it's the same sign. So we have that a plus b. And then the trinomial, when we have that plus, it's in the operations are in that palindrome format. So it's going to be like a plus, a minus, and then a plus. And then we have our a squared minus ab plus b squared. Once you have that all written on your paper, it's just being able to identify what is your a versus what is your b in this format. And we can write a cubed plus b cubed right below. So you can sort of very easily identify what is what, but we'll put it off to the side as well. So we have our a cubed is equal to our x cubed, which tells us that our a is x, right? And then we have our b cubed is equal to 64, which tells us that our b is, what's the cube root of 64? Yeah, good. Awesome. So now that you know your a's and b's, all you have to do is plug it into here and we're done. So we're looking at our a plus b, which is just x plus 4. That's our binomial. And then our trinomial, our a squared is x squared. And then a times b gives us 4x, so we have a minus 4x. And then our plus b squared, 4 times 4 gives you 16. And then we're done. Let's tackle this example 10 together. Now, instead of sums, we're looking at difference of cubes, which was that pink sort of highlighter. And so we have our whole a cubed minus b cubed. Again, the binomial shares that same operation. And then the trinomial is all positive. We have our a squared plus ab plus b squared. Now we're going to identify what our a cubed is. And our a cubed is just our 27 u to the third. which tells us that our A, well, what's the cube root of 27? 3. And what's the cube root of u cubed? It's just u. I'll use the same A and B colors. It's light pink and yellow. And then let's do the same for our B cubed. Our B cubed is equal to our 125 V cubed. So when we take the cube root of that, our B, what's the cube root of 125? Good, and the cube root of V cubed is V. So now let's just write this all out. We have our A minus B, so a 3U minus 5V. And then our A squared, 3U in parentheses squared is 9U squared. Our A times B, 3U times 5V is a plus 15UV. And then B squared, 5V times 5V gives you a plus 25V squared. And we're done. Any questions at all? No? All right. Let's keep going. So we have example 11. Now, example 11 here, what do you notice? Can we pull out a greatest common factor? Between 6 and 48, we can actually pull out a 6, but then what about our variables? Can also pull out a I. Yeah. And when we do that, what are we left with? X cubed plus 8y cubed. And that's where our sums of cubes comes into play. Again, that binomial is the same operation. And then what operation is for our trinomial? It's palindrome format. So we have a minus and then a plus. Our A here, what's the square root? Or not square root, what's the cube root of x cubed? Just x. What is the cube root of our 8y cubed? Just 2y. And so now let's substitute everything in. So we're looking at our a plus b, which is our x plus 2y, our a squared, which is x squared. A times b is a minus 2xy. And then our b squared gives you our plus 4y squared. And we're done. Any questions at all? Okay, let's look at this example. Kind of want to treat this x plus 5 as like your a. And so we're looking at an a cubed minus a b cubed, which is our difference of cubes. Binomial, the sign is the same. The trinomial, they're all positives. So a squared plus ab plus b squared. Let's identify our a's and our b's. Our a in this case is the cube root of x plus 5 cubed, which is just x plus 5. And our b is the cube root of 64 x to the third, which is just 4x. So now when we fully factor this, we get our a minus b, which is x plus 5 minus 4x. And then we have our a squared, which is our x plus 5 in parentheses squared, plus ab, which is our x plus 5 in parentheses 4x, and then plus b squared, which is a plus 16x squared. And we can actually simplify this a little bit more. This is sort of what I was foreshadowing to. That x minus 4x is a like term. So we're looking at negative 3x plus 5. And then that x plus 5 in parentheses squared is a perfect square trinomial dealing with sum. So this is just x squared plus 10x plus 25. And I'll maybe color code so you can really see what's going on here. And then let's use our distributive property to simplify what we have in blue. So we have a plus x times 4x is a 4x squared, and then 5 times 4x is a plus 20x, and then we have that plus 16x squared. We can combine some like terms. So negative 3x plus 5 is the same as just 5 minus 3x. Doesn't matter, you could keep it the other way. I just don't really like starting with negatives. And then we have an x squared, a 4x squared, and a 16x squared, which ends up with 21x squared. Then we have a 10x and a 20x, which gives us a plus 30x. And then we have our constant, which is a plus 25. Done. Questions at all? All right. So this is just a summary of what was covered today. It was a lot. We went through our difference of squares, which is our whole a minus b, a plus b. And then we dove into our perfect square trinomials, whether we were dealing with a sum or a difference. And then our last objective, we went over our difference and our sums of cubes, which again, I'll color code accordingly. I believe it was the difference was that pink, right? Yeah. And then the sum was the orange. So really try to make flashcards of these because it'll help you out a lot when it comes to assessments. These are some just extra supplemental material for section 6.3. I think this is probably one of the most challenging sections of the course, so I actually just recommend you doing all of the problems from the workbook in addition to the MyOpenMath. But these ones you should just definitely do. And then again, all of these notes are posted on Brightspace, and then I'll post the recording of this by today as well. That does complete our section 6.3. So on Wednesday, we will go into 6.5. I'll stop the recording now.